last part of the second order circuits is the step response, where you have a circuit, RLC circuit, that has source. So you see here we have the switch actually is connected. This means that the source is connected to the circuit. So you have a source. So this is not a natural response. This is what we call it here, step response. So the solution here will have a constant, which is called we call it the steady state. So for example, if you look at this circuit here, this circuit, simple circuit, and Vs is 10 volt. I know the value or the voltage across the capacitor, for example. What is the voltage across the capacitor? Finally, the voltage across the capacitor will be the same like Vs. Why? Because the capacitor is open circuit. When Vs is constant, is DC, the capacitor is open circuit. So you don't have a current at all. So the voltage across the capacitor will be the same like the voltage across the source, voltage of the source. So, and the current here, you will not have any current in the capacitor and the inductor. So the inductor short circuit, but the capacitor is open circuit, so you don't have any current. So I finally will be 0. So this is what we call a steady state solution. But what happened in between, this is what we call it here, you have a natural response. So it is actually like the previous one beside the steady state. So you will have some time between the initial values and the steady or the steady state values. Okay, so assume that it is, for example, the final value is 10 volt. Then in this case, it will vary. It will, for example, oscillate until it reaches a certain value, or can go like this or whatever. So let's check the solution here and see what is the difference in solution. For example, if we have this circuit, then in this case, of course, it is clear that we need to apply Kirchhoff voltage law because we have a closed loop. So we'll do the same. Okay. So here the voltage, this voltage is Ri. The voltage across the resistor is Ri plus L di by dt, the voltage across the inductor, plus 1 over C integration of I dt. This is the voltage across the capacitor equals the source, which is Vs. The problem here is what? That if we differentiate the whole equation, okay, to get rid of the integration here, in this case, you will get rid of Vs. So actually, you will cancel part of important data here, which is the source. So as if the source does not exist. So assume that Vs is 10 volt, 20 volt, 30 volt. When you differentiate it, okay, you will cancel these values, and you will lose it. Okay. So what is the solution here is that we try to find another way to get rid of the integration here. And to do that, we know that the current here, this current equal what? Equals C dV by dt. The current equals C dV by dt. Then we can replace this I by C dV by dt. Here you have differentiation and integration, they will cancel each other. Okay. So in this case, you don't have to do to cancel or to differentiate Vs, otherwise you will get 0 here. So in this case, this is L di by dt will be the same. Okay, Ri is the same here. This will be voltage here, the voltage across the capacitor. So we call this the voltage, just V, and we use this one here, I equals C dV by dt. Okay, and then substitute and divide by L. We substitute from this one to this one here. So di by dt, okay, is what? What's di by dt? Is C d square V by dt square. And Ri will be R C dV by dt. And dV is the same. Keep it the same. Not change it. Okay. So this is how we solve this problem here. So by doing that, you see here that the equation, instead of having an equation in current, we will have equation of in the capacitor voltage. So this is the difference between this solution and the source-free solution. In the source-free solution, you have for series, you have current. You solve for the current. Here you solve for voltage. So make sure that you understand this. So again, if you don't have any source, you solve for the current in series. Okay, in series you solve for current. But if you have a source, you solve for the voltage. This is the difference. You solve for the voltage. Okay, and the same also in the parallel. In parallel, if you don't have a source, you solve for voltage. If you have a source, you solve for current. We'll see this later on. Okay, so this will be the solution, the equation. You have d square v by dt square r over l dv by dt v over lc equal vs over lc. Okay, so this is the equation that we need to solve. So you see here, this equation is not equal to 0. It is a constant here. So the solution must have a part that will vanish, which is this part here, the transient solution and the steady state solution. The transient solution, when you say that this equals 0, this is a solution like what we did before. But the steady state solution is the voltage when t equal infinity. This is when you consider the capacitor open circuit and the inductor short circuit. This is the steady state solution. So the total solution is Vt, which is a transient, this one here, plus Vs steady state, or we call it S whatever here, Vs of t, okay, V infinity. So again, this is the solution. So if alpha, of course, R alpha and omega will be the same like in the series. There's no difference here. Alpha is R over 2L, here R over 2L, and omega is 1 over LC under square root. If alpha is omega more than omega, then V of t equal what? Equal A1 plus E1 S1t plus A2 S2t. Of course, this plus the steady state. You have to add the steady state. This is a VT, the transient solution. Plus, you add it to the steady state solution to get the final answer. So the idea here is the same like in the previous one. Okay, so we see V of t equal V transient plus V steady state. And the V steady state is V infinity. Let us take an example to see how it looks like. So look at this circuit here. The switch is turned off at t equals 0. So now look at the RLC circuit. It has resistor, inductor, capacitor, and it has this 24 volt. So now this is what we call step response. So this is different from the source free. It's not source free anymore. So we find the initial condition exactly like what we did before, and we solved this example before in the initial condition part. So V of 0 is 24 plus time 1 divided by R, this R plus 1. And dV of t equal this value here. Okay, so you see here we find the initial condition for voltage, not for the current, although the connection is in series. But when you have a source, we solve for the voltage, not for the current. Then we create the table. Okay, create the table. R is 145, 145, and L is 111, C is 0.25, and alpha is R over 2L. You calculate it, R over 2L, and omega 0 will be 1 over square root LC. Okay, and then you compare alpha to omega, exactly the same like what we did before, to decide what is Vt of t here. You see, this is Vt, the transient solution. Okay, the steady state is not difficult, because if you look at this circuit here, what is the steady state voltage? Because the capacitor, it will be 24 volt. Why? Because the capacitor will be open circuit, the inductor short circuit, so V steady state will be 24 volt. So this voltage here, you add 24 to this voltage, this will give you the total voltage. So again, you see here the steady state is 24. And you calculate V total using the V of t using this equation here. So VSS, which is 24 plus this one here. If it is under damped, if it is if it is critically damped, this is the solution for the voltage. If it is under damped, this is over damped, this is the solution for the voltage. We added this VSS, which is 24 in all of them. And we use the same equations to calculate the initial voltage here. Okay, so we see here V of 0, but here you have to consider VSS. See, V of 0 equal what? Equal VSS plus A1. Okay, so you just added a VSS. Why? Because this is V of t. V of t. So V of t, for example, equal 24 over 1 time time 1 divided by R plus 1. If R equal 1, so it will be 24 divided by 2, that's 12. Okay, so 12 equal what? 12 equal, substitute by t equals 0 here. So it will be VSS plus, this one is just A1 because cosine 0 is 1, plus A2 sine 0 will be 0, and e to the power of 0 is just 1. So it will be VSS plus A1. So VSS plus A1 will be V of 0, which is 12. If VSS is 24, then A1 will be negative 12. So this is how you calculate A1. So the only difference here is that you add this VS to V of 0. When you differentiate, you will not have it, because when you differentiate, constant is just 0. So you see you have VS here, you have VS here. Choose the equation. This is all what the difference between this one and the source free. So we have two differences. Number one, we solve for the voltage, not for the current. Second, we have this VSS. Okay, and we solve two equations to unknowns, or sometimes you don't have to solve two equations. Here you get A1 here, and then you substitute here to get A2. Same for this one, but here you have to solve two equations into unknowns to get A1 and A2. Okay, so this is the solution for this example. See here how the solution look like. See how the solution look like, to just get an idea what is damped, what's critically, what is over. You see, over damped, you see it is increasing like this, and it will reach a steady state value, which is 24. Supposed to be 24. Why it is seems to be close to what here? I don't know. Supposed to be 24 here. Okay, so the value supposed to be 24. Okay, so the steady state value is 24. The over the critically damped, it will increase rapidly here. You see, it will reach the maximum rapidly. Okay, you see, but after that, right after the critically damped, it will start to oscillate like this, and then at the end it will converge to the final value, which is the 24. Okay, so this is just to give you an idea how the voltage look like in underdamped, this underdamped, okay, oscillation, critically damped, and overdamped. Okay, so overdamped is sometimes take more time to reach the maximum. Okay, than critically damped, of course.